All right, so welcome back. We are in chapter 17, section 4. So that means we are working with LaGrange multipliers. And so here's our next problem. Our job is to look for a relative maximum of a given function subject to a constraint. So what makes this different than last section, section 17.3, is over there we look for everything everywhere, and we never had constraints. And what I mean by everything everywhere is we were looking for the maximums and the minimums and the saddles, and we looked for them all using that discriminant test. We're in chapter 17, section 4 now, where we have something slightly different. We're looking for either a maximum or a minimum, so we're ignoring saddles, and we have this constraint issue, this idea that we have some restriction upon what the variables can be. And in this case, our restriction is that whatever x is and whatever y is, when I add them together in this way, their sum, that is x plus 2y, must always be equal to 15. So we're looking for the maximum possible value for this surface, this three-dimensional surface, where the sum of the x and the 2y must always add up to 15. Right? So let's go ahead and get started. Let's work through this process using LaGrange multipliers. The first thing we need to do is we need to take that constraint and rewrite that constraint correctly. Right? Under Lagrange multipliers, the constraint is a function g of xy that must be set equal to 0. So the first thing that we need to do is we need to take that function, that constraint, and rewrite it properly. That is that our g of xy will be equal to x plus 2y minus 15. Right? All right, so now that we've got the first step in the Lagrange multipliers process completed, that is, we have our function's constraint written correctly. Now we'll build the Lagrange function. The Lagrange function is big F of your independent variables, in this case x, y, and our dummy variable lambda, which we'll use to help us solve for those points we're going to go look at. Right? Now, by definition, that is going to be equal to the function f of xy, that is the function that we are looking to optimize, plus lambda, I'm sorry, plus minus, minus lambda times g of xy. Right? Or in this case, when I replace the function notation with the proper variables, we get that x, y squared minus lambda times x plus 2y minus 15, or distributing out, we get x y squared minus lambda x minus 2 lambda y plus 15 lambda. All right, at this point, we've got our Lagrange function correctly created. The next step of the process is to create the partial derivatives for our Lagrange function. So we have three partial derivatives that we have to look for. We have to look for the partial derivative with respect to x. And when I take that partial derivative, there are, I believe, it looks like we've got 1, 2, 3, 4 terms in our Lagrange function, and the partial derivative of the first term with respect to x will be y squared. The partial derivative of the second term with respect to x will be a negative lambda. The partial derivative of the third and the fourth term are both 0 because there is no x variable. Okay. Now we have to find the partial derivative with respect to y. The first term will give us 2xy for our partial derivative with respect to y. The second term will give us a 0 because there's no y variable in that term. Our third term will be negative 2. That's a bad 2. Let me clean that up. Negative 2 lambdas. And our fourth term will have a 0 partial derivative with respect to y because there's no y in that term. Now we'll take our third partial that we have to do, that is f sub lambda. That is the partial derivative of Lagrange function with respect to lambda. First term 0, second term will be a negative x. Third term will be a negative 2y. And the fourth term will be a positive 15. Right? Now, if you've done everything correctly, a quick little check here that kind of lets you know you're on the right track is that the partial derivative with respect to lambda should be the opposite, that is multiplied by a negative 1, the opposite of our g of xy. And it's looking like it is, so it makes me feel, isn't a guarantee, but it makes me feel like I'm doing the right thing. The next step is to create a system of equations where we set all of these equal to 0 and solve. Now I'm just going to repeat what I did last time because it worked. And what I mean by that is I'm going to take these two and solve each of them for lambda, and then set those lambdas equal to each other. So let's go ahead and do that math. In the first one, we get y squared minus lambda is equal to 0, which means that lambda is equal to y squared. So that's from that first partial derivative. If we take a look at the second partial derivative there, and we solve that one, we're going to get then that lambda equals xy. Right? The 2's will cancel, right? Maybe you want to see all the steps, so let's go ahead and just rewrite that and do all the steps. We're going to have 2xy minus 2 lambda is equal to 0, which means that 2 lambda is equal to 2xy, but then we can divide both sides to remove that 2, and we just get then that lambda is equal to xy. Right? Now I haven't used this third one yet down here, and I'll use it later, but right now I'm just going to focus on the two solutions that we're looking at right now. Okay? We're looking at lambda could be y squared or lambda could be xy. Now the lambda is the same. That means that both of the left-hand sides are equal, so therefore, by the transitive property of equality, the right sides must be equal, or y squared must be equal to xy. And then that is now what we're going to use to solve for one of the variables. That is, we have the statement that y squared minus xy equals 0. So y times y minus x is equal to 0. And now I'm going to make use of something called the zero product property, or the zero product principle, that says that if two things are multiplied together and the answer is 0, that one or the other must be 0. So at this point, we know that either y is 0 or that y minus x is 0, which means that y must be equal to x. So those are our two possibilities right now for our variables. And I'm going to take this information and use it here in that third partial derivative to find values for the other variable, if you will. Right? All right, so first case is that if y equals 0, then negative x minus 2 times 0 plus 15 would be equal to 0. And so we would get that negative x plus 15 equals 0, or that x must be 15. Now remember, when I started this purple that I'm writing right here, I said that y had to be 0, so that means that one possible solution is that x is 15 and y is 0. Okay? Now the other possibility was that y was x. So then I'm just going to replace all the y's with x's. That will give us, if y equals x, then negative x minus 2x plus 15 would be equal to 0. Right? Remember, I'm using this third partial right here, so all I did was replace that y with x. So that gives us what? Negative 3x plus 15 equals 0. That would mean that 3x is equal to 15, or x would be 5. Okay, so x is 5, and our supposition there was that y is the same thing as x. So if x is 5, then y must also be 5, or our second possible solution is the 0.55. Now, if you're wondering why I keep saying possible solution is, I go back up here to the top, we're supposed to be looking for the relative maximum. Now, Lagrange is good, but Lagrange also has a limitation in that it doesn't tell you those points that we found. It doesn't tell you what they are, whether they're the maximum, the minimum. They both might be maximums. One might just be bigger than the other. So our job now is to explore those possible solutions and determine which one is the thing that we're looking for, in this case, the maximum. The way that we're going to do that is we're going to go back to our original function that we were supposed to maximize, which was x, y squared, and we're going to evaluate it for those 2 points and see which one does the thing we want it to do. In this case, which one gives us our maximum. So let's take a look at that first possible solution, f of 15, 0, which give us 15 times 0 squared, which is a big fat 0. Now, is it possible that 0 could be the largest value for this function? It most definitely is, but I'm going to check the other one as well. What is f of 5, 5? Well, f of 5, 5 is 5 times 5 squared. I'm just using the function right there. Let's see, 5 times 5 squared. 5 squared is 25. 5 times 25 is $1.25. Now, when I compare these two, I'm looking for the maximum, and it's pretty obvious at this point that 125 is way bigger than 0. So our relative max is at the point 5, 5 with a max value. Remember, the max value is the functional value of 125. Right? Now, depending on what the question asks, sometimes the answer is just this, sometimes the answer is just that, and sometimes the answer is all of it put together. Are they just asking for the coordinates of that maximum? Then 5, 5 would be the answer. Are they asking for the relative maximum value? Then 125 is the answer. Or are they asking for both? And so keep an eye on the directions. Make sure you're answering the question that they're asking. Because if they want the 0.55 and you type in 125, the system's going to mark it wrong. And I get that you're not wrong, you just read the question incorrectly. So just be careful with that. That's a common mistake. Okay? All right, moving on. Let's take a look at another problem. It's a little more complicated, but at its core is the same problem. All right, so we have a cereal box with a fixed volume of 185 cubic inches. The end of the box is a square. Our job is then to find the dimensions of the box that would yield, oh, what happened there? Oh, a minimum surface area. Okay. Now, I don't know about you, but I'm a very visual person, so I'm going to sketch this out and see what's going on here. I have a box, and the end of the box is a square. So I've got something that looks like this. Excuse my poor artistic abilities, but the bottom of the box is a square. So this side and that side have the same length. I'm going to choose to call those dimensions x. So that's going to mean that this side down here is x, this side over here is x, but this side over here, there's nothing in the problem that tells me that that has to be the same value. So I have to give that a different variable name. I'm going to call that side y. And so I have a box that is x by y. Remember, the bottom two sides have the same dimension because the box is a square. Okay? The vertical, if you want to call that, the height, is a different variable because nothing in the problem tells me that this has to be the same on all three sides. Okay. Now, my job is to find the dimensions that minimize surface area. So I need to minimize surface area subject to, because I do have a constraint here, the volume has to be 185 inches cubed. Okay? So now I need to build some math so I can do that. Since my job is to minimize surface area, I need to build a surface area function. That is, my little f of xy has to be the surface area function. Now, how do I find the surface area of a box? Well, if I take a look at what's going on over here, if I were to take out a pair of scissors or a box cutter or whatever and slice this box up, I would get four sides that all look like this. They're all x by y. And then a top and a bottom that were squares that were x by x. So that means that my surface area function is 4xy plus 2x squared. The 4xy is the four sides, which have an area of x by y. It's a rectangle, base times height. The top and the bottom, that gives me my 2x squareds because the area of the top and the area of the bottom are x by x or x squareds. Okay? Now my constraint is that the volume has to equal 185. Now the volume of a box is the base times the height, the length or the area of the base times the height. So my volume, which has to be 185, will be x squared y. Right? Now if I rewrite that correctly for Lagrange, that would mean that g of xy is equal to x squared y minus 185. Good so far? Okay. So now I've got a function that I want to minimize. I have a constraint, so now it's time to do Lagrange. Okay. First step in Lagrange, after you've got your functions, that is your constraint function and your max or min function, the first step, or next step, if you want to think about that, is to build that Lagrange function. Okay, that means I'm looking for f of x, y, lambda, which is equal to your function f of xy minus a lambda times your constraint g of xy. So let's see, f of x, y, lambda is going to be 4xy plus 2x squared minus lambda x squared y plus 185 lambda. Okay, once we've got our Lagrange function, our next step is to find our partial derivatives. So we need to find f sub x, our first partial with respect to x. Right? In my Lagrange function, we're looking at 1, 2, 3, 4 terms. Okay. The first partial with respect to x of that first term will be 4y. The first partial with respect to x of the second term would be 4x. The first partial with respect to x of the third term will be negative 2 lambda x y, and the first partial with respect to x of the last term would be 0. There's no x in it. Right? Moving on, now we'll find the first partial with respect to y. First partial with respect to y of the first term will be 4x. First partial with respect to y of the second term would be 0. There's no y in it. Third term will be negative lambda x squared, and last term has no variables, so no y variable, so it has a partial of 0. Okay, f sub lambda. First term with respect to lambda is 0. Second term with respect to lambda is 0. Third term with respect to lambda is negative x squared y. Fourth term with respect to lambda is positive 185. I'm going to do that same little check I did last time. Is this guy the opposite of that guy? Yeah, looks good. All right, so now it's time to do math. I need to set this system that we just created. I need to set all of these guys equal to 0 and then solve. I'm going to do the same thing that worked last time. I'll solve the first one, the partial with respect to x for lambda. I'll solve the second one, the partial with respect to y for lambda. I'll set the algebra equal to the algebra. I'll solve for x or y and substitute into the third. The process, pretty much the same every time. All right, when I solve that first one for lambda, I've got 4y plus 4x minus 2 lambda xy is equal to 0. That gives me 2 lambda xy is equal to 4y plus 4x. I'll divide both sides by everything that isn't lambda, and that's going to give me that lambda is equal to 4y plus 4x, all divided by 2xy. But I think I can factor a 2 out of all that to clean it up even further, and that would give me then that lambda is equal to 2y plus 2x divided by xy. And that's all from that first one. Okay. Now I'll do the same for the second one. Okay. The second one is going to give me then that 4x minus a lambda x squared is equal to 0, which means that lambda x squared is equal to 4x, or that lambda is equal to 4x divided by x squared, or 4 over x. Right? Now, since this lambda is the same as that lambda, by the transitive property of equality, that algebra must be equal to that algebra. And so I'm going to set those two algebras equal to each other. So let me just kind of carve out some space over here and say then that, whoop, don't slide on me, 2y plus 2x divided by xy must be equal to 4 over x. Since I have a statement that a fraction on the left is equal to a fraction on the right, I'm going to cross multiply. When I cross multiply, that's going to give me 2xy plus 2x squared is equal to 4xy. Moving this term from the right to the left would give me then that 2x squared minus 2xy would be equal to 0. I'll factor on the left. I've got 2x times x minus y is equal to 0. The zero product principle would tell me that this means that either x is 0 or x equals y. Okay. Looks similar to last time, doesn't it? Okay. I'm going to take these two now and put them into that third partial and see if we can get values for them. Right? The first possibility was be if x is indeed 0, then we would have, what does that say, negative x squared y plus 185 equals 0. So negative 0 squared times y plus 185 equals 0. Now, I don't know about you, but isn't this 0? And how could 0 plus 185 equal 0? And that just doesn't make any sense to me. So while it is an algebraic solution, it is not an actual solution to the system. We have a fancy name for those things. We call those extraneous solutions. Okay? All right, so that one's out. So then hopefully this one will give us something meaningful. Otherwise, I don't know what we're going to do. So the second one says, if x equals y, then what would possibly happen? Well, if x equals y, then I'm going to get negative x squared times x plus 185 equals 0. So I just took this and replaced that y with x because x and y are the same. A little bit of math here, and I'm going to get then that x cubed is equal to 185, which means that x would have to be equal to the cube root of 185. I'm not sure what the cube root of 185 is, so I'm going to have to bring up my calculator. So give me a second here to make that happen. Let's see. I'll pause. All right, through the magic of pausing, we're back and we've got a calculator up. So now I can say, okay, what is 185 raised to the 1/3? And it looks like it's about approximately 5.7. So that means that x is approximately 5.7. But remember, our supposition here was that x is equal to y. So that means that y would also be approximately 5.7. All right. All right, at this point, I'm at the one problem, the issue that we have with Lagrange. I found a point, I found dimensions for this box, but I don't know if those dimensions give me a maximum or give me a minimum because Lagrange doesn't tell me. So what I need to do is I need to come up with a second point that also satisfies the constraint, and I'll use it to check and see whether this point is a max or a min by comparing. All right? Now remember the constraint up here said that the volume had to be 185. So I'm going to just make up a point that satisfies that so I can use it to compare to the point that Lagrange found me. Now I'm lazy, so ideally I'd want to pick one of my variables to be 0, but I'm never going to get that to work. So I'm going to do the next best thing and say, well, if x was 1, then y would have to be $1.85. And that'll be the point I'll use. So my compare point will be the point 1, 185. Now, what I need to do is I need to take both of these points, that is this one and my comparison point, put them into that surface area function and see which one of those will minimize my surface area. Okay, if you remember, the surface area function was this one, the 4xy plus 2x squared. So my surface area function that I'm trying to minimize, my f of xy, that was 4xy plus 2x squared. Now I'll check it for 185 first because I have to do both of them, so I'm just doing that one. So that's going to give me 4 times 1 times 185 plus 2 times 185 squared. I'm going to use my calculator for that. So let's see. 4 times 1 times 185 plus 2 times, whoopsie. Let me fix this before it's a mistake. That's x, so shouldn't that just be a 1 squared? So, well, 2 times 1, which gives me a surface area of 742, and this is surface area, so that would be inches squared. Now, I don't know what that means yet because I'm using that to compare to that solution right there. So now let's check the other one. F of, let's see, how exact do we need to be? Well, how about I use the cube root of 185, comma, the cube root of 185. So that's going to give us 4 times the cube root of 185 times the cube root of 185 plus 2 times the cube root of 185 squared. That's definitely a calculator problem. So I'm going to come over here and say 4 times, let's see, where was it? Is it here? Here? Here. No. There's somewhere where there's a shortcut to the cube root function. I can never really remember where it is. I don't know. I guess I'll just use this. 185 raised to the 1/3. And that'll work. And then times another 185 raised to the 1/3. Oops, that parentheses is in the wrong place. And then plus 2 times the quantity 185 raised to the 1/3. But then I need to square that. And when I do that, I get approximately 194.8. And remember, this is surface area, so these are inches squared. Now, my job was to, what was my job again? Oh yeah, my job was to minimize surface area. So the point that we found with Lagrange gives us a surface area of 195 approximately square inches. My comparison point shows me that 195 is smaller than 742. So it looks like If I wrap this all up and make it look pretty, the dimensions that minimize surface area are approximately 5.7 inches by 5.7 inches by 5.7 inches. Effectively, we've made this box into a cube where all three dimensions are the same. All right, I'm going to end this one here because it is getting kind of long. So 30 minutes, but I hope that you understood everything I did. And if you have any questions, again, always please reach out.